Hello everyone, welcome to this talk. I'm Zine Elabidine. 5 years ago, I was a Java programmer in Tunisia, in North Africa, where I was born. And the team decided to change the Java project to Scala. So we decided to learn Scala. Along the way, I heard many scary terms in functional programming, and I was quite lost. But even though I was really interested to learn more and to understand things, it wasn't easy there. So I decided to travel the world and explore Scala opportunities and join events to learn more about functional programming and Scala. So today I'm going to share with you what I have learned, and I'm going to talk about functional programming paradigm and how could we define types and functions, and how could we implement type classes, and mention some algebraic data structures like Monoid and Functor and Monad. Let's start. First of all, to understand what is functional programming, let's understand what is a paradigm. A paradigm is a style and a way of writing your program. Each programming language follows a programming paradigm, and Scala follows a combination of object-oriented programming, which belongs to imperative paradigm, and functional programming, which belongs to this declarative paradigm. In order to understand how a paradigm could affect our ways of thinking and reasoning about anything, about the code, and in real life, let's say an example, how could it happen? For example, Daniel and Sophie would like to buy a house. Both of them, each of them have different way of thinking. Daniel was thinking, how could he buy a house? He did his researches, he checked out his bank account, and he talked to his family and his partner and tried to figure out how could they pay the charges, etc. And then he informed the architect to make a design for this house. At the same time, Sophie was deeply focused on what she wants, exactly the home that she wants to have. Then, when she found it, she asked about what she needs to do to reach this goal, and she provided the resources. So here I presented two different mindsets. Sophie was thinking in declarative mindset, which based to on the question, what I want to do. And Danielle was thinking in imperative mindset, which based on how I can do it. As a first step to learn about functional programming, we can think like Sophie, what I want to do in order to solve this problem, because functional programming is a form of declarative programming paradigm. So, and functional programming is about programming with functions and compose them together. Each function has inputs and outputs, and these inputs and outputs are data. The data are immutable. In order to change the behavior of the data, we need to pass them around functions, and each function will build new data with new behavior, because we cannot change the state of the data. And all of these functions in functional program have to be pure. A pure function means that it should satisfy three important criteria. The first thing, it should be total, which means we can know what to expect from a function by looking to the input type and the output. We can reason about the function from its types, and we can, yeah, like for example, Sophie, like if we describe the situation as a function, as an output would be a house, and as an input would be the resources to provide. And now we know what to expect even without looking to the detail of the implementation. And the second property is a function should be deterministic. When for every input, we should have a result, and we should have the same result when we pass the same inputs, which will help us to test our program without unexpected behaviors. So whenever we pass a function with the same inputs, we should have always the same result. And the pure function should compute its result using its input, and it shouldn't do anything else than computing the result. And this is what we call the function is free of side effects. If we have a deterministic and free of side effects functions, we can say that this function is referential transparent, which means that we can replace the function with the result of its evaluation without changing the meaning of the program. Like, for example, when we call sum with specific inputs, we can change this with its result without having any unexpected behavior, because the function doesn't have any side effects. It will only do what's supposed to do. So now it is clear why would we choose to use functional programming. It gives us many benefits, like testability. We can test our functions easily because they are deterministic, and we can also, it makes it easier for us and for our colleagues to review our code. It is easy also to refactor the code by just reasoning about the function from its inputs and outputs and trusting the function that it will do what's supposed to do because it respects these criteria. Now we saw how, like, we cover how what is functional programming and why would we use functional programming. Let's see how could we define types and use them and define functions in Scala. Because Scala is a statically typed language, it provides type checking during compile time, which helps us to provide correct programs. And it is easier to reason about our programs using types. And most of functional programmers says, if it compiles, it works. What is algebraic data type? ADT is a type formed by combining other types. For example, simple types like int, string, double, boolean could be combined in a structure which will have different values in a single structure. And this type of structure called product types. String, when you settings, when you see setting, you say, okay, setting has audio enabled and video enabled fields. So it makes sense why it's called product, because and when we like each fields settings has both of them, and also it's helpful to reason about what, whenever you see something of type setting, it is easy to expect what you would have as settings. You can say, okay, settings have two possible values of for audio and two possible values for video, and we multiply these possible values and then we expect 4 possible values. This why here I am mentioning this, because to see how could we reason about our code just by seeing, look into the type, so we can adjust our expectation. Now, for some types, this is another algebraic data type, and some types are types where your values must be one of a fixed set of possible values like enumerations. So this sum type is defined using seal trait. This is, we can do this and we extend this trait. A trait in general is like interface, and all of these are the member of this sum type, and we are using sealed. Sealed trait helps us to have exhaustivity check in case to check if all the member of this trait are located at the same source file. Then when we see something of type color, we know what to expect. We are going to have one of this value, this or this or this or this. This is why it's called sum type. And also, if we would like to compute how many possible values, we can say this is like, it is 1 plus 1 plus 1 plus 1. And also we can have an algebraic data type that is a product type that uses sum type like this. Here, when we see form, we would expect that we have infinite values for topic and for possible values for color. And we can also try to say, okay, I would like to have specific expectations, so I can improve this algebraic data type by specifying which kind of topics that we can have. And here we define another sum type topic, and we use it in form, so we can know what to expect in form. We can have 4 possible topics and 4 possible colors, and we multiply these possible values to have 16 possible values. So this is to see how could we reason about just looking to the type and adjusting our expectations. We can also have parameterized algebraic data type, and the possible values for this depends to this parameter type. And in case if you see, for example, option of Boolean, you know what to expect. You have some true, some false, or none. Also, if you have option of int, you can know what what to expect. Many values of int and none. Now we see how could we define types and what are algebraic data types. This will help us to because we are using in functions, we are using types as input and output. Now let's see how could we define functions. And it's important to learn about how could we define functions in Scala, because basically we are going to have functional program, which is the practice of composing programs using pure functions. So using the keyword def, we can define our functions and specify the input type and the output type. And then here we implement the function. And Scala has first-class functions, which means we can see a function is defined as a data type. When you see a function, for example, that takes as an input int and returns Boolean, this is itself a type. We can also associate a type alias to it, for example. And we can also use literal syntax to define our functions. And this is what we say, we call it lambda. And here it is anonymous function. We can also associate a value for this. And because functions takes data as input and data as output, they could be also other functions. If we have a function that has function type as input or as output, we call this higher order function. For example, check option is a higher order function. It takes a predicate which goes, for a given integer, it checks, it returns Boolean, and then we can, for example, check if the predicate is satisfied with the value of the option. Now, how we call this? We can associate a value for this function, and we call it. And because we are using just the input here, we can replace it underscore. If you see this, it means that we are using the input without any need to do this. Also, we can call the function directly using literal syntax. And the same, we can use underscore here in this case. Nice. After we see how could we define functions and data types, let's see how could we add functionalities to our types in a functional programming way. There is this pattern called type classes. It is a way to define certain operations for a given type. A type class instance for a given type provides an implementation for these operations. In case if we think in oriented object, we use interface to add features, and whenever any type, if any type would like to take this feature, we can extend this interface. Let's see how it would be using interface. We can define, for example, translator interface that provide to us this feature translate. But when we look to the type signature, we cannot reason about. It's like everything is of type string. We cannot know what to expect. So let's improve this, and for a given source, we are going to translate from a language to another language, and we will return the translated source. So we can make from and to as a type called language. It would be a seal trait that could be either English or Japanese, and we can add more languages. We can also define source. A source could be different things. It could be like, it is the choice of the programmer. If we want to add the feature to a specific source, we can take this type, and it should return the same type. So let's make this type a part of the interface. Now, for example, if ScalaMatsuri wanted to, organizers wanted to use Discord auto translation bot, we can make or like provide implementation for translate for the Discord message and use it in our program. And this is, we try to make it a little bit functional by defining a program that takes as an input a Discord translator. If we would do this as in oriented object, we would directly inside, like for a given Discord translator, we can use translate directly in that interface. We are trying to make it better. And then if we would like, for example, to translate a simple text, it is the same. We need to implement the translate for string, and then we use it. And the same for documents, the same for audio. And it would be the same for anything else. It's the same program with different implementations. So let's make it better and not repeat ourselves by making a polymorphic program that will accept any kind of translator, and then we use this function from the translator. So we use this feature. Now let's make our parametric interface a type class. The first step is to add apply that will help to abstract over different data types that have similar structure as translator and returns the concrete type to access the method translate. So here, when we call this translator, we will have access to translate without any need to have the inheritance from translator. We directly using this translator dot apply, we can access translator. How we do this? Here we call the translator object dot apply of the type A, and then we call translate. Here we accessed our feature, and then because apply requires implicit translator, this using context bounds guarantee that there is an implicit implementation for translator of A. It is the same, it is just a syntax for having implicit translator. Now, how could we define the implementations for the translator? We call this type class instances. For a given type, we can define implicit value that takes the implementation. And then we can call the program with specifying the type that we would like to use. And then the compiler will take care of this. We'll check if there is a type class instance for this type. Nice. Now we are ready to cover algebraic data structures. These, like semigroup, monoid, functor, monad, all of these are, you can see them as type classes that provides their algebra, their own algebra. What it means algebra, they support different, different operations, and they have to follow or to respect specific laws. They are not just simply a type. No, they have specific operations that can offer to us, and they have to respect specific laws. Now, for example, semigroup provides combine method, and this has to satisfy associativity law. Like, for example, the addition operation of integer, it satisfies this law. So we can say that int forms a semigroup. When we will define combine, we are going to use plus A plus B to implement this type class instance of semigroup. Also multiply respect associativity law, and string, the concatenation, and also Boolean. Even if we have our types, we can make them, they can also form a semigroup in case only if they satisfy associativity law. Now let's see monoid. Monoid is a semigroup. It has the combine, as we already saw, and an additional method, empty. Combine should satisfy associativity, and also empty should satisfy identity law, should be a neutral element of our types. For example, if we combine A with empty, we should have an A. We shouldn't, empty shouldn't affect the result. For example, if we consider multiplication for an integer, two integers as a combine, we can the empty element would be 1. 1 multiplied by anything equals the value. And also, when we would like to combine, we would like to add two numbers, the empty element would be 0, etc. So if we would like to have our customized type, our own type that we defined, and we think that it could be a monoid, they definitely should respect these laws. They should have empty elements and they should be associative when we combine two of these elements. Now, let's see functor. It is not the same like semigroup and monoid. It doesn't have just an A. It has a type constructor with one type argument. For functions, if we have function that has another function as input, we say that it is a higher order function. And for types, if, for example, functor has a type constructor, we can say functor is a higher kind of type. Functor provides a map method that will, for a given f of a, it will apply a function that goes from A to B, and then we return f of b. Functor should satisfy the identity and the composition laws. The identity wouldn't be the same as monoid. It is not a simple one element. It is the identity function. For a given A, we give, for a given A, we return the same A. So map should satisfy this law. For the map of identity, it should be equals to identity. Whenever we will define a type class instance for an implementation for functor for a specific type, we should make sure that it will respect the identity law and or the composition law. What is composition actually? For a given f that goes from A to B, and the function, and if there is a function that goes from B to C, there should be possible to have a function that goes from A to C, which is the composition of f and J. So, and this is how, it is like this if we would like to compose two functions. And when we call compose, it is like, if you would like to compose f with J, this is the syntax, how we do it. And map should satisfy the composition law in this way. Let's take an example to understand it better. For example, option forms a functor under map method here, and here when we define a map for an option of A, we should return option of B. So we are, in case of none, we return none. In case of sum of f, we apply the function to this element. When we pass a function, identity function here, we are going to have, this is f, it would be from f to f, it will return the same result. So in case of none, it's none. In case of sum, it is sum of f of a, which returns a. So this is the identity of option. So option satisfy the identity. The map function in option satisfies the identity law. For composition, let's take, for example, a function that for a given int, it increments the int, and another function toString, it makes the int string just. And if we call map, then the composition of increment and toString for sum 41, the result of this, it would be sum of 42. And if we compute the result of map increment, which would be sum of 42, and then we compose it with map toString, it will be equal to sum 42. So this satisfies the law, composition law. Now let's see monad. All monads are functors. They have the map function, and monad is higher kind of type like functor. And the additional operation is flat map. Flat map for a given, for a given f of a, we take the value of a and build a new f of b out of this input. And we can also add point, which is also could be called pure. This is a unit value of a monad. For example, if we have a monad of type option, point would be the sum of 42, for example, and because it will build a simple value of this type, f. Now let's see the laws that we need to satisfy in order to make sure that, okay, our type could be a monad, could form a monad. It should satisfy identity law and associativity. Let's see, it is not like we are basically will check the flat map function. So let's take the example of option, but we are going to use directly the flat map of option. And if you see here some of this is we are going to construct or to build an option that it is like we are calling point. For example, if we have sum of 42 and we flat map and we call function increment with 2 and not without using this this a, it should return the result in the right hand side. So because here this would be this is satisfy the left identity law. And for right identity, to check if it is right identity, the sum, it's like we are calling the point, the method point in monad. If we call the method point in flat map, this is the right identity. It shouldn't affect the result of the sum 42 of the initial value of this monad. And for associativity law, this should satisfy, we can, for example, sum of 42, we can call flat map increment and flat map decrement. We can also, it should be equals, it shouldn't, the value, the result shouldn't be different to a flat map, and inside this we do both operation, increment and decrement. And this is how we verify if our types could take the functionality of monad, functor, or any other algebraic data structure. There are more. I try to cover these. There is also applicative, but I didn't add it here. It adds the other operator. It is zip, but I know that the time wouldn't be enough for this. But to see how monads function in real life, this is a tweet by Igal. In general, monad or functors have this type constructor. You can consider it as a box. And for a monad, we can have we can compose our boxes together and to build new boxes. So yeah, now like you are, I hope that it was clear for the algebraic data structures and the type classes. You can learn more if you would like to learn more about functional programming, and you can check out CAT's library. In the documentation, you can also learn more about different type classes and algebraic data structures that CATs offer. Also the same for ScalaZ. And you can check out Zio Prelude. It is a new project. And if you are interested about, you can check out the talk by John DeGoss and Adam Freezer. And if you'd like to learn more about CATs, you can check out the talks of Jakub Kozlowski and many other talks. And yeah, at the end, if you feel that, yeah, I learned and it's quite cool, you will find out that really functional programming is awesome. And I hope that you think this way, at least most of you think this way. Yeah, and that's it. There are more things to learn, and yeah, I hope that you enjoyed this talk. Thanks a lot, and thanks to ScalaMatsuri organizers for their help and for this opportunity.
はい、ウィームズ・イラビリンさん、発表ありがとうございます。時間がありますので、質疑応答に移ります。これより Discord のトラック A チャンネルに書き込まれた質問をピックアップします。まず、モダドに慣れていない立場だと、使おうとするのが難しく感じるときがあります。慣れるために必要だと考える方法や意識していることがあったら教えてもらえますか？という質問があります。大丈夫かな？私は日本語で喋らないといけない。今現在、Discord の方に、ウィムさんが直接回答をしてくださっているのかな？
There is a question in Discord. Should I answer it here or should I write it down? There is a question about if you are new to monads, you may find it difficult to use them. Can you tell me how to think it is necessary to get used to it, or if there is something you are aware of? I usually, to understand, in general, I see monad like flat map, and you have a type constructor, and if you implement by yourself the flat map function that for a given input, it's like you have a container, and for the element of this container, I would like to build a new container and applying a specific function to it to turn it into another, doing some operation, but build a container inside this. I hope that it is clear. But I personally learned about Monoid is using I implemented by myself different kind of map for for different types. I tried to implement flat map for them, and then also and then it's automatically I got used to that.
Exactly. 次の時間が、迫っているので、質疑応答はこれにて終了いたします。続きは休憩時間中か、懇親会にてお願いします。また引き続きトラック A チャンネルで質問を書いていただければ、Wiem さんの方が拾ってくださると思います。以上をもちまして、このセッション終了いたします。画面上では見えないかもしれませんが、拍手の方をお願いいたします。では、ご視聴いただきありがとうございました。